Let's make this more realistic. Where things are not going to work out as nicely. And no matter where we picked our axis of rotation, we should have gotten the same answer. I've got the beam one more time. Rotating about the rotation point. I've got this, and we'll keep that at 0.2 meters. 0.45 newtons. And then over here, 0.8 meters, so we'll make this 0.47 newtons, and we have the weight, which is at 0.48 meters, and let's make it a magnitude of 1.01 newtons. Oh, that 0.8 meters is that distance there. The forces up do not equal the forces down, because this is similar to what you would get in a physics lab. Look, that is farther off than I was hoping. You should get closer. Probably some scale did not get 0 probably. I'm going to change that 5 there to a 9. So first off, let's just take a look at forces, as we just talked about. I'm going to keep this condition here, so up, to the right, and out. So my total force acting on the beam would be 0.49 newtons plus 0.47 minus 1.01. And negative 0.05 newtons. That symbol I have in front, this right here just means sum. I just got a little lazy in my notation there. This is just the sum of my, I probably should put sum of forces. What I would expect on the lab is that number to be close to 0. So, somewhat reasonable. Now, I'm not expecting there to be a perfect, if I add up the torques, I'm going to get 0, but I should be getting something close to 0. But we still need to pick a pivot point. What I'm going to do is pick, I'm going to pick where the left force scale is. I'm going to pick this to be my pivot point. And now I'm going to add up torques. So what is the torque from this 0.49 newtons about to this point right here?
Zero.
Indeed, it is not going to rotate this thing one way or the other. So I have 0 plus. This next one, I've got a moment arm from my axis to where the force is applied. That is going to be 0.28, the difference between that and that. So positive 0.28 times the force of negative 1.01. That's meters and newtons. Or I could have figured out that negative sign just by up here. Which way is that force trying to rotate this? Well, it's trying to rotate it clockwise, which is into the board, which is negative by the convention over there. And then the last one, plus. So I've got 0.47 going up. That's my force. My moment arm a vector for my axis to where that is applied, which is 0.6. And if someone would be kind enough to do that calculation. Shout out the sum when you get it.
Negative 0.0008.
Negative 0.0008.
Square.
Anyone else get the same thing? All right, I just heard a nod there. That's all I know. All right, pretty darn close to zero. What would the units be, by the way? Yes. Pretty darn close to zero. Now, ideally, they'd be equal to zero, but it's pretty darn close. All right, I'm about to make the problem look more complicated. Any questions? All right. Being what? Let's say 1.01 joules. That is 0.48 meters. That is 0.2 meters. That is 0.8 meters. We have some mass hanging right there. Let's make this 1.5 newtons and 3.7 newtons. All right, I have no idea if the numbers are going to work out as nicely as they want them to, but we're still going to work through the process. I want to figure out what that mystery mass is. I make it look like it's a force there. It's not a force. I have some mass hanging here. It has a weight, which is acting on the string, which then acts on the beam. I can find that weight two different ways. I can do it by sum of forces, and I can do it by sum of torques. In a perfect world, I'd get the same answer. In this world, well, probably going to be a lot farther off than you'll be on the lab. But let's first do it by sum of forces. If this thing is in static equilibrium, I know that sum of the forces should be zero. I'm going to stick with that convention right there. So I have 1.5. This is my sum of forces. Plus 3.7 minus 1.01 minus my mystery weight, and that equals 0. So I have 1.5 plus 3.7 minus 1.01 minus equals my weight. Actually, I'm going to change that slightly. I'm going to make that plus my weight. So we add up what we know here. let's see, 1.5 plus 3.7 is 5.2, so I get 4.19. Now the negative there, because I did plus W here, the negative there is telling me that it's downwards. When I had the negative there, I'm sort of automatically assuming it's downwards, and I would have gotten a positive value, which we already assumed is down. What I did here is I add up the known forces. And that's the sum of the known forces. Therefore, the vector weight would be negative 4.19, indicating that it's downwards. But the magnitude of my weight would be 4.19. So I would write my weight, 4.19. But I'm trying to find the mass. What does weight equal? What is the formula for weight?
Mass times gravity. Force of gravity.
Right. You would have written it down correctly, but the wording was off. What did you say?
Mass times acceleration to the right.
Yeah. mg is also a lot easier to say. Equals mg, acceleration due to gravity. So my mass, so I have 4.19 is equal to my mass times, in a lab, 9.798. I'm trying to find mass, so I need to get that 9.78 over to the other side. Because it's held on by multiplication, I have to undo it with division. And so we end up with a mass of 0.4 something. 0.437. What is it?
Yeah, 4.427.
427. Units?
6. Kilograms.
Yeah, kilograms. All right. So I have the mass using sum of forces. I have an answer. Now in reality, I would be able to figure out, I could measure the mass of my mystery and I could do a percent error based on that. Now let's use sum of torques. See how close we get to the same answer. Well, we have to pick an axis of rotation.
The far left.
Far left. All right. Using the I hat, J hat. So that produces that moment arm is a vector from here to here, so it's a magnitude of 0.2 meters in the I hat direction. So I got 0.2 times 1.5 plus the next one is the weight of the meter stick. That's 0.48 times negative 1.01. Then I've got plus 0.7 times this. Now, it is a vector downwards. If I want a positive weight, then I would put in negative W there. If I just put in W, I'll end up with a negative number. Unless I did something really bad with the numbers over there. And then the last one, it is 0.8 times 3.7. That equals 0. now it's a matter of doing the parts we can do. So we got this, this, and this. I'll take the first one, 0.3. And if someone else would be kind enough to,
Negative point forty,
negative point
40,
40,
48, 48.
48, 48. Okay. And the last one? One more time?
2.96.
2.96 equals 0. Let's go ahead and add up the parts that we know there, the parts without the W in it.
Okay, altogether I got 2.7752.
2.775
52.
52 equals 0. Still solving for W. I need to get W by itself, so first I have to get those terms over. So I'll pop that one over there. So I had negative 0.7W is equal to negative 2.7752. Now I need to isolate W, so I divide both sides by 0.17, so W is negative 2.7752 divided by negative 0.7. And I end up with 4.19. You got what?
3.96.
3.96. To find the actual mass that would cause this, set that equal to mg, that's 9.798, since we're pretending this is an actual lab. And so my mass would be 3.96 divided by 9.798.
Like 402 kilograms.
And that is somewhat realistic, you know, how far those off are, and there's two different techniques. Questions still there?
Can we use I have J hat all the time instead of the right hand?
In a problem like this, yes. I hesitate all the time, but, yeah. All right. I'm done with torque at the moment. You know, I assume she's leaving because we were gonna talk about something other than torque and she's a fan. Let's talk about the fact that acceleration, what is the formula for acceleration, vector acceleration? I heard change in velocity over time.
Over change in time.
Okay. How does velocity change? If you're driving a car, what are the 3 accelerators?
The gas pedal, the brake, and the steering wheel.
Yes. So I can change my velocity either by changing speed, speeding up or slowing down, or by changing direction. So far, we have dealt with changing of speed. I don't think we've done changing of direction yet. So let's now talk about this acceleration because of change in direction. Well, we're gonna sort of try it conceptually here. If I've got a road here, and you are driving along, looking for a particular road, but you're driving too fast, and suddenly you realize that this is the turn you need to make. What is going to affect how hard it is to make that turn? All right, how fast you're going. So the faster you're going, the easier or harder? Okay, so speed would affect it. And what else?
How close you are
To the,
to the turn, like how close are you?
that versus that? Okay, the radius of curvature is the math physics term for it. Yeah, so how tight of a turn you're making and how fast you're going. So for this long arc right here, we have a much longer radius, and here we have a much shorter radius. Shorter radius, easier or harder to make the turn? Okay, so if radius goes up, it should make it easier. If the speed goes up, it should make it harder. So that sort of gives some indication of how we are going to form this. So this acceleration, and put a little subscript c next to it, is going to be equal to the speed squared. And not justifying why the squared is there, just sort of trust me. I'll be glad to go through the derivation if there's a desire for it.
No. Thank you.
Divided by the radius. So if r goes up, if we get a much more sweeping turn there, so instead of, we're not jerking the wheel tightly, so if r goes up, my acceleration goes down, which means it requires less force.